Okay, this is Dr. Williamson. I'm going to show you guys how to use, this is just a quick little video, show you guys how to use Appendix B and how to calculate values of the Gibbs free energy for this particular reaction, where delta G is equal to delta H minus, that's supposed to be an H, minus T delta S. That little circle means under standard state conditions. Okay. Right. So over here, we have Appendix B. And I've sent this to you guys, posted in the announcements. I've told you guys to have it printed, have access to it. Really a good idea to just have a paper copy of this for when you do your homework. There's two ways we could calculate the Gibbs free energy. We could calculate it by getting the delta H values and the entropy values, and then calculating delta H and delta S, assuming we know the temperature we're running the reaction at. Or we can just straight look up the delta G values and calculate it that way. We're going to do it both ways here. Okay. So what I need to do is look up the delta G and delta S values. So I'm going to put, let's see here. Let's put the delta H values on this line, the entropy values on this line. It's supposed to be an S, not a 5. And the delta G values here, right? And then what I'm going to do is scroll over to the table. And let's see me look up. Oh, wait, where's hydrogen? Might as well look up hydrogen first. Carbon, LM. Here, hydrogen. I've got hydrogen right here. And when I go up, notice the circle doesn't move. The first column is delta H, next column is G, next column is S. HGS. So let's remember that. So hydrogen, the value of H, so this is H, delta H. This is delta G. This is S. Value of delta H for hydrogen is 0. Value of delta G is 0. And the value of the entropy is 130.6. Notice it's S, not delta S. Okay. So we have that. Now let's go over here. We have nitrogen. Okay. I'm going to leave these delta H, delta G, delta S to kind of help me remind here. All right. So for nitrogen, it's going to be 0, 0, and 191.5. And then for ammonia, they have these values, right? So for ammonia, delta H is negative 80.83, 80.83. That's supposed to be 80.83. Oh, wait a minute. I made a mistake. That was aqueous. I want gas. See, this is gas over here. So I'm glad I made that mistake, actually, so I could point it out to you guys. All right. So I need to use the correct value for the correct state. So it's negative 45.9. Negative 45.9. And I got to have the right units also. Okay, delta G will be positive 26.7. And oh, wait, I see I did it again. I did it again. I looked at the wrong column. All right. So it is negative 16. I looked at the wrong column. That's how I miss points on tests. And then this is positive 193. 193. All right. And what are the units now? Okay. Where's my mouse? The units are, this is, let me just here. This is kilojoules per mole. Delta G is kilojoules per mole. And Kelvin is joules per mole Kelvin. Excuse me, entropy is joules per mole Kelvin. Okay. So first I'm going to calculate the Gibbs free energy of this reaction just using the delta G values first. And I'm going to type it. Okay. So let's do this. Type. I'll just use that. So I'm going to go here. Delta G standard conditions is equal to, now it's going to be the products minus the reactants. So I'm going to have 2 times negative 16 kilojoules per mole products minus here 1 times 0 plus 3 times 0. That's a little bit redundant. Okay. But I did that as a teaching tool. All right. So I'm going to have 16 times 2. That's 32. So I'm going to get negative 32. Negative 32 kilojoules per mole, or negative 32 kilojoules is my Gibbs free energy when I calculate it that way. Right? When I do the delta H and delta S, I should get very similar to the same number. And we're assuming a temperature of 298 Kelvin, right? So now we're going to calculate, let's calculate delta H. Delta H under standard conditions going to be here 2 times the product minus 45.9. All right, products minus reactants minus, and the reactants are going to be here. Oh boy, I'm just sitting there. You guys are watching me. And 1 times 0 plus 3 times 0, right? That's equal to 45.9 times 2. And I'm going to get negative 91.8. kilojoules per mole, or kilojoules. All right. Delta S under standard conditions is going to be equal to products minus reactants. That's going to be 2 times 193 minus 1 times 191.5 plus 3 times 130.6, going to be equal to, say, 193 times 2 equal to minus 191.5, okay, minus 3 times 130.6. I get negative, I hope I did it right, negative 197.3 joules per Kelvin, right? Because I'm multiplying by 2 moles and 1 mole and 3 moles, joules per Kelvin, which is equal to negative 0.1973 kilojoules per Kelvin. It would make it all consistent. So then, assuming 298 Kelvin, 25 degrees Celsius, I'll do this in a different, this delta G in a different color. So I'm going to have here delta G naught, because it's going to be from these, will be equal to delta H minus 91.8 kilojoules, right, negative that, minus 298 Kelvin times negative 0.1973 kilojoules per Kelvin equal to negative 91.8 kilojoules minus 298 times 0.1973. Okay, that should be a plus now. Plus 58.8 kilojoules, because the kelvins canceled, equals and I get negative 33 kilojoules, which is the same value. Okay. So this, calculating it directly from the table and calculating it through delta G equals delta H minus T delta S, gives me the same value within rounding errors, guys. Okay. So I wanted to show you that. I'm actually impressed I didn't make a bigger math error, like get a minus sign mixed up or whatever. But anyway, I just wanted to show you guys how that works. And I'll show you guys more stuff later. Okay, then.